Let's try and finish Module 3 now. This is the third lecture. If you recall the last lecture, we began to look at the idea of looking at complex numbers and graphing them. And we did this sort of funky thing where we decided we could graph, we'd have like the real part and the complex, or the real part and the imaginary part of the number, and we could graph them. And then if we graphed it, we decided, wow, we could actually write these complex numbers with polar coordinates. So just as a quick review, rectangular, if z is like a complex number, we said, well, x plus y times I. If we write the complex number polar coordinates, it's r, and in parentheses, cosine theta plus I times sine of theta. Right? So we did all this last lecture. But now we're going to do something else. Now we're going to take, say we have two complex numbers, and we want to multiply or divide them. Now there's two different ways we can go about it. We can do this multiplication or division with both complex numbers written in rectangular coordinates. Matter of fact, let's just do one now. Let's just say I have a complex number written in rectangular coordinates 3 plus I. I'm going to call the second complex number W, 3 minus I. Now this is a pretty simple case, so you can see hopefully that if we were going to multiply these, we could just do old-fashioned multiplication. 3 times 3 is 9, plus 3I, minus 3I, minus I squared. 3I minus 3I cancels out. Remember I squared? I squared equals -1, so I'm subtracting a -1. So it looks like if I multiply those together, it equals 10. Now here's what I want to do. We can also multiply complex numbers together if they're in the polar form. And there's some special equations, and you might ask yourself, well, this looks pretty simple. Why do we want to do it? Well, sometimes it's not so simple, or sometimes you may be given some complex numbers and polar coordinates, and to try and convert them back into rectangular and to do the multiplication is like a pain. You just want to go ahead and be able to multiply numbers in polar coordinates. So let me give you sort of like the formula. Actually, I'm going to give you the formula both for multiplying two. So formula, so this is when the complex numbers are in polar coordinate form. So easiest way to do this is I'm going to call my first complex number Z1. Of course, this is the standard form. So I'll call this R1 and theta 1, so we know that makes up the Z1. So I'm basically just going to write out the equation of a complex number in polar coordinates. Then I'll call the second complex number Z2. So it's R2. All right, so I'm doing this so I can give you the formulas. So now, if you have two complex numbers and they're both written in polar coordinates and you want to multiply them, It's just a quick little nice formula. What you do is you simply multiply the two r's, r1 times r2, and then you have the cosine, and inside the cosine you simply add the two angles plus I, and then you take the sine and you add those two angles, and you've got it. So in other words, if you're given two complex numbers written in polar coordinate form, it's actually pretty easy to multiply them together. And then in a minute we'll also do, you can divide two complex numbers. Now this might make sense to you, but when we multiply complex numbers, we multiply the r1 and r2, what do you think we might do here? Yep, we take r1 divided by r2. What do you guess we might do here? Here, if we add the angles together, you know what we do when we divide? Cosine of theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So what I'm going to do just for fun, just to prove that this works, you know the example I did up here where I multiplied z times w in rectangular and got 10? Let's go ahead, just for fun, let's convert both z and w to polar coordinates and then use our formula here and multiply those complex numbers as polar coordinates, and hopefully, if we don't make any mistakes, we should get 10. We'll see. So here's the first one. This is rectangular coordinate. If I were to do polar coordinates, right, we've done this many times before, I got to figure out my r, which is x squared plus the y squared. Looks like square root of 10. Theta is inverse tangent y over x. So let's put this in degrees. We have to estimate it, but hopefully it'll be okay. Inverse tangent of 1/3. Let me call it 18.43 degrees. So now I can say z, written as polar coordinates, is square root of 10 cosine 18.43 degrees plus I sine of 18.43 degrees. And now, if w as a complex number is 3 minus I, r for this going to be square root of 10 again. Now how about theta? Minus 1 over 3. This is going to be a little trickier because the inverse tangent is negative 18.43 degrees. If you think about this, if I, just to visualize this, if I had to graph this, 3 and negative 1, it's like right here. This is in the fourth quadrant. So my angle, that's my angle. This right here is negative 18.43 degrees. I'll call that prime because my real angle is not going to be, you can see if I take 360 degrees minus 18.43. My angle is really 341.57 degrees. So here's my, this is a lot of work, but it's good practice. Here's my z vector, or z complex number. Here's my w, once again, square root of 10, except it's cosine 341.57 degrees plus I times sine. I'm going to rewrite this because I'm running out of room. So we figured out the two vectors. In polar coordinates, z is square root of 10 cosine of 18.43 degrees plus I times sine of 18.43 degrees. And in polar coordinates, figured out w is square root of 10 times cosine 341.57 degrees plus I sine 341.57 degrees. Now, I'm going to multiply them. They're in polar coordinates. So I can use my equation here. What do? You multiply the two r's. Square root of 10 times square root of 10 is 10. And then you remember what you do? You take the cosine, you add the two angles. So 18.43 plus 341.57 360 degrees, and then it's I sine, and you add the two angles. But let's look, cosine of 360 is just 1. What's the sine of 360? If you multiply those two vectors, you get 10. And if I look back, when I multiplied them in rectangular coordinates, it's also 10. All right, so I did that just to show, okay, yeah, this formula works. If you have two angles written in polar coordinates, this is the formula to multiply them together. Now let's go ahead just for practice. Let's just go ahead and divide these. So division, remember, then you take the first r divided by the second r. Instead of adding the vectors together, now you're going to subtract. So actually it's going to be 18.43. This is going to be interesting. 18.43 subtract 341.5. Whoops. 18.43 subtract 341.57. Negative 323.14. Plus I sine of course this is just 1. So it's basically this. Looks sort of ugly, and I guess if I wanted to, I could convert these into numbers. So 323.14. The cosine of that is like 0.8. and negative 323.14. The sine of that is like 0.6. So if you divide them, you get something like this. Or if you want to leave it in polar coordinates, just like that. All right, so that's something else now we can do with complex numbers. We can multiply them and divide them. And whether you're in rectangular coordinates or polar coordinates, we've learned now, if you're in polar coordinates, we've got these special equations that make it pretty easy to do. And here's another special, and this is named after, I think it's some French guy. If I try and use my French pronunciation, Demois, probably. He must have came up with this. And here's the idea. Let me get you the big picture of Demois' formula and see why it can be helpful. Sometimes, maybe we want to take a complex number and we want to raise it to a power. What do I mean by that? Say we have, here's my complex number, 3 plus I. And say for some reason we need to know z to the 7th. Meaning we take that complex number and we raise it to the 7th power. Now, if you wanted to do it to the old-fashioned way, you could take 3 plus I, this parenthesis, times itself 7 times. I don't know, it may take you 20 minutes to do that multiplication. However, this Demois came up really, it's almost like a shortcut, an easier way to figure this out. And the shortcut is, what Demois discovered is, or what he came up with is that really 2 steps. First, you're going to take the complex number and you're going to rewrite the complex number, not the exponent, just the complex number. You're going to rewrite it in polar coordinates. And you're going to see once we rewrite it in polar coordinates, we can apply this little formula that Demois came up with. And then once we do that, if we want to, we can convert back to rectangular coordinates. So the idea here is almost, if you take a complex number written in rectangular coordinates and you want to raise it to an exponent, especially if the exponent's like a bigger number, if you try and leave the complex number in rectangular coordinates, this is a real pain to do. But you're going to see in a minute this little shortcut where you take your original complex number and you rewrite it in polar coordinates, which we can do. We've done that before now. Because once you have the number in polar coordinates, we can apply this special formula. And this special formula gives us a very easy way to calculate the complex number raised to a power. And then when we get done with that, we just convert it back and we're done. So let's just go ahead, like most things, once you see it being done, you realize it's not too difficult. Let me go ahead though and let me give you this formula that this Demois came up with. So when we get ready to use it, we'll know what it is. So here it is. Here's the number. Here's the standard way we write a complex number in polar coordinates, right? There it is. What Demois says is, okay, you're going to take a complex number and we're going to raise it to a certain exponent, a certain power. What does this equal? He found out that it just equals, if you take the r out here and you apply the exponent to it, and you take cosine, whatever your theta was, you make it n times theta plus I sine n of theta. You're going to see, I'm going to prove to you how using this Demoivre's formula makes this kind of problem so much easier. All right, so let's do an example. So here's my complex number. And what I want is z to the 7th. Now just to make it very clear, if I try to just leave this complex number in rectangular coordinates, basically it's going to take me a minute, but I just want to make it very clear to you what kind of 1, 2, 3, 4, 5, 6. Can you imagine foiling these two, then taking that times this and this? I mean, it would probably take you maybe 20 minutes or half an hour to do that. That's what we call painful. However, let's try this shortcut. The shortcut says you take your complex number and you rewrite it in polar coordinates. So here's the complex number. Remember, this is like my x and my y. Remember, complex number is going to be r cosine theta plus I times sine theta. Need to find r and theta. Remember, r x squared plus y squared for us. The x is 3 squared, and the y is 1. And theta is the inverse tangent of y over x. Inverse tangent of 1 over 3. I think we've actually done this vector before. So 1 divided by 3, inverse tangent, 18.4 degrees. So now z, written in polar coordinates, is going to be r square root of 10 cosine of 18.4 degrees plus I sine 18.4 degrees. Now what Demoivre's theory says that, okay, if we were to take this to the 7th power, what do? We take r and we raise it to the exponent. All right, so this is my r here. So square root of 10 raised to the 7th power. And then cosine of n times theta. Once again, n is 7, so cosine of 7 times 18.4 degrees plus I times sine 7 times 18.4 degrees. Let's just go ahead and change these in numbers. So I'll take square root of 10, raise it to the 7th power. It's going to be a pretty big number, actually. Three 162.3 cosine 7 times 18.4, 128.8 degrees, plus I sine. Okay, compare all of this to what I did here. Now granted, my answer is still in a polar coordinate, and now if I want to change this to rectangular, what do? It's pretty simple, right? Remember, x is r times the cosine let's just go and do that. Cosine times 3162.3 negative 1981.5, and y is r times the sine so 128.8 the sine times 3162.3 equals 2464.5. 2464.5. So basically, in rectangular coordinates, we have negative 1981.5 plus 2464.5 times I. Now this may have seemed like a fair amount of math, but trust me, if you tried to do this, you would still be working probably for another 15 minutes. And you would probably be making all kinds of math errors. So once again, what are we doing here now? We're taking a complex number, we're trying to raise it to an exponent. This is painful. The de Moivre formula says, okay, take your original complex number, write it in polar coordinate form. So in this, our example, here's the polar coordinate form. And then when you apply de Moivre's theory, it's not too hard. You just take your r, raise it to the power here, the power here. Now you actually get your answer in polar coordinate form, and then we know how to switch it back to rectangular, and there it is. All right, so that's one interesting little sidelight of stuff we're doing. Now actually, I think I need to go ahead and probably take a break for the last part of Module 12. So let me stop now. Looks like we're going to have one more video to finish out this module.